The final type of thermodynamic cycle that we will discuss is called a heat pump. Let's consider a cycle on the PV or TS diagram that again goes counterclockwise. We know from our discussion of refrigerators that a counterclockwise cycle has the ability to absorb heat from a cold reservoir and eject heat to a hot reservoir. But in the refrigerator, what we cared about, what we considered as our benefit of running the cycle, was to cool the cold reservoir, remove heat from it. In a heat pump, the cycle is still counterclockwise, and it's virtually identical to a refrigerator. The only thing that's different is we change our perspective on what is the cost of the cycle and what is the benefit. Let's look at the energy diagram again for a counterclockwise cycle. By using some work input, we're able to move heat from the cold reservoir to the hot reservoir. In a refrigerator, we considered QC to be the objective of running that cycle. In a heat pump, our goal is different. We want to heat up an area by using this cycle. So our cost is still the work input that's required, but this time our benefit is heating up the hot reservoir. It's like if we took an air conditioning unit on a cold day and turned it around in the window so it blew its hot air into the room and kept its cold stuff outside. We could use this to heat up our room, and that's what a heat pump basically does. The different meanings of cost and benefit for a heat pump give us a different definition for its coefficient of performance. We take the ratio of the heat ejected to the hot reservoir divided by the work input that's required. This is our COP for a heat pump. If we construct a heat pump from the ideal Carnot cycle, we'll find out that its coefficient of performance is equal to the temperature of the hot reservoir divided by the temperature difference between the reservoirs. This formula, I won't derive it explicitly, but it's not unexpected since we've just sort of switched the assignment between TH and TC. It looks a lot like the COP for a refrigerator. We can also show that for any other heat pump cycle, its coefficient of performance has an upper limit that's set by the Carnot value. So heat pumps can be quite effective at moving heat between two locations. Again, we have a ratio of a temperature to a temperature difference. So if the room you are trying to heat is around room temperature, and you want to establish a small temperature difference of maybe 10 or 20 Kelvin, then your coefficient of performance can be much larger than 1. It seems a bit counterintuitive, but we can use a small amount of work to induce a much larger flow of heat between the reservoirs, as long as the temperature difference is small. This makes heat pumps very effective when you want to slightly heat an area in an environment where the temperature difference won't become too large. Heat pumps are used to heat houses in southern climates, heat the inside of garages, or as heating sources on boats.